Okay, let's have a look at the structure and bonding within organic molecules, and we're going to start with alkanes. So alkanes are completely saturated hydrocarbons. They have carbon atoms that are singly bonded to each other, and therefore there's no extra room for addition of more hydrogen. So that's where the word saturation comes from. They generally have the formula CnH2n plus 2. So an example of this would be CH4, which is methane, or C2H6, which is ethane, and so on. That's for the open chain compounds. The rule changes as soon as you make cyclic molecules, which have CnH2n overall molecular formula. So, and that makes sense if you have a non-cyclic molecule, and at the ends of that chain, we need to make a new bond between one carbon and another carbon atom that are saturated. We have to be removing a hydrogen from each one to make that new bond, and therefore make it into a cyclic molecule. Like that. So generally alkanes have very free rotation around each carbon-carbon bond, except in those cyclic systems. The ring systems, the connection of the whole group of atoms into a ring means that there's restricted rotation, and we don't get this free movement and rotation. So long hydrocarbons that are not cyclic can actually exist in all sorts of different shapes that we call conformations. We'll talk about that more in another video. Okay, so looking at the properties of alkanes, they're fairly consistent. They generally have higher boiling points the longer the chain, and this is a fairly consistent rise with these unbranched linear alkanes. So methane is very low boiling, minus 161 degrees, whereas when we get up to decane, we're looking at a boiling point of well over 100, so 174 for N-decane. They're non-polar molecules, so there's lots of ways of saying that a molecule is non-polar. We can say they're non-polar, lipophilic. We can say that they're greasy, is a very common term that's used to talk about non-polar molecules. And the only forces between the molecules are van der Waals forces. So this is London dispersion forces, or the force that dominates the interaction between non-polar molecules. So the boiling point increases, as I said, as you go up in chain length. The geometry of organic molecules is really related to their three-dimensional structure of carbon and the fact that it's tetrahedral. So carbon has 4 valence electrons, and so after it's been hybridized, we have an sp3 hybridized system. And sp3 hybridized atoms are tetrahedral, and so in the simplest alkane, that should be alkane, by the way. So let's just in the simplest alkane, methane, the carbon atoms that are bonded to each of those hydrogens, there is overlap between the carbon sp3 orbital and the hydrogen 1s orbital, forming each one of those sigma bonds. In ethane, there's one carbon-carbon bond, which is between an sp3 orbital on one carbon and an sp3 orbital on another carbon. And so that gives ethane its overall shape over here. So all of the bond angles in alkanes are tetrahedral. So they're very easy to predict what the shape of these molecules will be like. So the covalent shape that you get from the overlap of these orbitals is So the covalent bond that you get from overlapping these orbitals is called a sigma bond. So sigma bonds are where we have end-on overlap between orbitals. And that is the strongest type of bond that we can make. So in alkenes and alkynes, we have another type of bonding called pi bonding, which is a side-on overlap between p orbitals. So whilst most of the molecules represent as static drawings, that's the easiest way to represent them, obviously, on a piece of paper, rotation around these single bonds is very easy to occur. And so these molecules are constantly shifting in shape, trillions upon trillions of times per second, normally, at any reasonable sort of temperature. If we freeze them down to very low temperatures, like near absolute zero, then we can freeze out into a single shape and we'll get rid of this rotation, but that's certainly not the case at room temperature. So each one of these shapes, each one of these three-dimensional arrangements of the atoms through the way that their bonds are rotated is called a conformation. And each one of the different conformations are also known as conformational isomers. And we'll talk about isomers a bit more in a moment. So if you look at the connectivity of organic molecules, we can actually have the same number of carbons and hydrogens in an alkane, but yet get different molecules. So if we look at a C5 molecule, we can have N-pentane. So this molecule here should be called N-pentane. The second molecule below it, we've moved one of the carbon atoms along the chain to make it what's called a branched alkane. So this is now a branched alkane, whereas this is a linear or unbranched alkane. So isopentane is where we've got a branching point, and then neopentane is where we've got a highly branched molecule. So it's got one central carbon atom surrounded by 4 methyl groups bonded to that central atom. They're all C5H12. They all have the same molecular weight, but they're different molecules and they have different properties. So the boiling point of N-pentane is 36 degrees. And in fact, you can use this as a solvent in the lab. And I've used it in the lab myself if we need a non-polar solvent. It's very low boiling point, so it's very easy to evaporate. However, isopentane is even lower still. So at ordinary sort of temperatures you get in southeast Queensland, this molecule is quite difficult to keep in the liquid form. However, not as difficult as neopentane, which generally is either a gas or a compressed gas or a liquid under some pressure, because the boiling point is only 9.5 degrees. And so the connectivity in these C5 alkanes has an influence, it has a bearing on their boiling points. And it has a bearing on many of the other properties as well. So each of these molecules has the same chemical composition, it has the same atoms, but they're arranged in a different bonding arrangement. And so they have different chemical and physical properties. So they would also have other properties that are differing as well as just their boiling points. And so we call this type of difference between molecules with the same molecular formula, we call this connectivity isomerism. And they're connectivity isomers. What does that all mean? Well, isomerism is just a phenomenon where certain compounds can have structures that are different, even though the compounds possess the same elemental composition or the same molecular formula. So isomers are what show this isomerism. So 2 or more chemical substances can have the same composition of elements, same molecular weight, but different in their actual structure. And the number of structural isomers increases dramatically as we get more and more atoms in a system. So there's only one molecule that has CH4, that's methane. There's only one way of connecting 2 carbons and 6 hydrogens, and that's ethane. There's similarly only one way of connecting 3 carbons and 8 hydrogens, it's propane. However, once we get to 4 and above, then we get larger and larger numbers of possible isomers where we can move these atoms around the system to make various branched and cyclic molecules. So this is known as isomerism. There's different types of isomerism. What we've talked about so far is known as constitutional isomers. We've called it structural isomerism. Constitutional isomers is the more common term. There's another whole branch of isomerism known as stereoisomers. So this is where we have molecules with the same molecular formula, but they have different three-dimensional arrangements of the atoms. So they're connected to each atom is connected to the same atom as the other members of the isomeric series, but there's a different three-dimensional way of arranging those elements. Now, stereoisomers is a big field. There's a lot of different types of stereoisomers. But for the sake of this video, there's just going to be one that we're going to look at. So if we go down this path over here from stereoisomers down to diastereomers, don't worry about this term at the moment, but down here to conformational isomers, quickly talk about that. Okay, so conformational isomers differ from constitutional isomers. Constitutional isomers, we're talking about a different arrangement of the bonding within the molecule. You can further subdivide that if you like. It's not a common sort of set of terms, but sometimes people talk about positional isomers, where we move, for example, a functional group to different places within a molecule. So the molecules have fairly similar properties then because they have the same functional group. Or maybe we have, say in this example, a benzene ring with two methyl groups but in different positions around the ring. But the other common type of constitutional isomerism is functional group isomerism. So we have the same molecular formula, same atoms in the molecule, but they're bonded in such a way you have different functional groups. So for example, cyclohexane is C6H12 and 1-hexene is also C6H12, but they have quite different properties because one is a cyclic alkane and the other one is a acyclic alkene, and they'll have different reactivity and different properties. Now back to that idea of conformational isomers. So conformation is related to the three-dimensional shape of a molecule. So, and it results from how different rotation around CC single bonds affects the shape of the molecule. So we've already seen that conformational isomers or conformers result from this type of rotation. There's a couple of ways of looking at conformational isomers. One is to draw Newman projections. So here's a picture of Newman over here who developed this way of looking at them. There's also sawhorse diagrams, and both of these are useful in different ways. So a sawhorse diagram, we draw a bond between the two carbon atoms that we're interested in, and then we draw the substituents in this kind of pseudo three-dimensional arrangement. And we can see how the arrangement of one carbon atom interacts with at the other. So what's drawn here, if we then look at that molecule and pretend that we're looking along a line, there's your eye looking along that bond there. So there's an axis here. We imagine looking along that line that a Newman projection is a way of looking at that conformation where we take the front group and we draw in the three groups using our normal sort of lines, and then we draw a circle that signifies the back atom, and then we draw the remaining three substituents around that circle. Okay, and so in this particular case we would call that a staggered conformation of this molecule. If we then rotate around this bond here, then we're going to get to a different conformation, so a different three-dimensional arrangement of the atoms, where we have these atoms close to each other between the front and the back carbon atom. So A and D are very close, C and F are very close, and E and B are very close. And we call this an eclipsed conformation. So these two conformations around the CC bond are quite likely to occur, but they're not necessarily of the same energy or the same sort of degree of favorability. So Newman projections can be used to illustrate these different conformations around when you rotate around a single carbon-carbon bond. For example, in butane, we've got a C4 H10 molecule here. If we draw out different conformations of that molecule and then draw out the Newman projections, we can see there's some conformations where we have atoms or parts of the molecule that are eclipsed, and there's others where we have bigger groups eclipsed. So this just has hydrogen and methyl groups eclipsed. This one has two methyl groups eclipsed. And we can also have staggered arrangements like this, where all of the groups on the front and the back carbon are as far away as possible from each other. And it turns out if you plot the energy of those conformations, and we imagine going from one to the next along a continuous sort of change in angle around that bond, then we get each of these staggered conformations are minima on the energy diagram. And each of the eclipsed conformations are maxima on the energy diagram. The worst eclipsed is where we have the two methyl groups close together like this. And the best staggered arrangement is where the two methyl groups are as far apart as possible. And there's been a lot of work in trying to quantitate this, and we know the energy differences between those different conformations. Okay, so that's all we're going to say about isomerism for the moment. But hopefully you've got an idea now that there's a constitutional isomers where we take the one molecular formula, the one set of atoms, and we change the connectivity. So maybe we go from unbranched to branched alkanes. And conformational isomers where we have the same connectivity of atoms, but we arrange them in a different three-dimensional arrangement that we can get integrated from one to another via rotation around single bonds. Okay, thanks for watching.